Hello. Very nice to be here. And it's my nth time in China. And I'm very happy about this invitation. Last year, my team, our paper got some award, but I was not able to come. So I guess this year I will talk a bit about this and other things, right? And so just before I start, I would like to tell you where I come from. This is, okay, then maybe this is BIFO. I'm at Technical University of Berlin, and we have one of the 5 national centers for AI in Germany. I'm very happy to direct it together with my colleague Volker Marke. So I'm the machine learning part of this center, and Volker is the big data part, database management side. Because lots of problems these days contain a lot of data or streaming data or things like that. And one interesting aspect of our center, because there are centers all over the world, so we get 22 million euro, that's nice, but also we have a permanent funding, and that's even nicer, which means that all 7 years people come knocking at our door and see whether we have messed up, but if we didn't, then we can keep going, which allows us to think very long term. And some of what I'm going to tell you about is long term. Okay, so I guess the other way. Okay, so because I will talk about insights when applying machine learning in the sciences, it's really important to really understand, and I will tell you what this means, and this gives us the field of explainable AI. And then I will talk about the science, which is quantum mechanics, and you've been exposed to quantum mechanics in the morning and quantum field theory and all the great things, so I will add to this a bit, right? So when people use neural networks, then most of the world is very skeptical, because these are models with many, many parameters. And the question is, can we understand what's happening inside, and can we gain some knowledge? And I will come to this. We are now in a very interesting time. So because we have a lot of data, sometimes not so much data, but anyway, we have data, and we can try to train models so that they can make good predictions. But we can also have the techniques to understand what's happening in the models, so we can learn from the models afterwards. We can learn things that we didn't know before. And that is in medicine, in quantum physics, where I demonstrate this, and in other disciplines. So our paper in 2017 was maybe the first one where we actually could show this practically. Okay, so let's first start, okay? So any one of you have a neural network, and it's nice, it's trained, the weights are fixed, it's predicting very well, so you're happy with it. The problem is that, of course, this neural network is deep, has many layers, and it's very nonlinear, okay? So now you make a prediction. For example, this neural network has been able to learn what the difference between a car and a cat and a dog, like the typical things in computer vision is. So now it knows about roosters, right? So now it gets a new picture of this rooster. And so it says correctly it's a rooster, right? So it classifies this correctly, although it has never seen this picture before. So the model is good. So now what you want to do is you would like to know what's the strategy of this model to understand this, so to make this prediction. And there's a slight problem, which is this is a nonlinear function. So in a way, if you want to know what is the reason for this prediction, then you would like to know this in terms of the input features that you put in that case, the pixels of the image. Okay? So you would like to know what in the light of the trained model makes this a rooster. Okay? So here is the hard part. This is a nonlinear function. So in principle, you would have to put a nonlinear function upside down. And that's hard, right? So it took a while, but in 2015, we had the first paper on this. Well, in fact, the second one, the first one was 2010, but then 2015 was a solution that we could also theoretically understand. It's called layer-wise relevance propagation. And basically, we can now inspect the model, and the model, this layer-wise relevance propagation algorithm, the explanation algorithm, tells us that most pixels don't matter. They are green, okay? It's a heat map here. Some of them are red. So these red pixels, they are the ones that the model thinks are important for this prediction. So you can now relate this to the rooster, and basically it's the rooster's comb over here, which everybody can relate to. So the model apparently, by seeing many roosters, has understood that roosters have a comb, and then for this particular case, it says that for this particular thing to be a rooster, it's important to see that it has a comb. Okay, so this establishes some technique that we can use, and I will tell you a bit about how this works. So in a neural network, you put in an image. So an image has many pixels, so you have many input units, as many as pixels. And then you have several layers, and from each layer to each layer, you transform, you warp, you non-linearly do things with it, and you do this for a while, and then it's called a deep neural network. And in the end, you have the output layer, which tells you an activity, and you can see the model thinks this is a ladybug because the activity is high for that one, low for cat and dog, just for the illustration purpose. So that's the forward pass of a neural network. We know that. So just to emphasize very much, so the neural network is trained. All the weights are fixed. Okay? So now I explained to you the relevance propagation. So basically, we have to put the model upside down. And we do this by saying, well, all the activities that we have in the output layer, we call them relevances. Okay? So now that's this equation. Then we say, how about computing the relevance in the next layer below? And we do this by taking the weights that are fixed, right? W, multiply them with the relevances, normalize them, and multiply them with the activity that we had in the forward pass, from the forward pass in this particular node. Now this looks a bit strange, right? This is like an algorithmic hack, but it is not. We can prove that this is, the mathematically right way of doing things if we are thinking of the neural network to be a very high-dimensional decision function in the space of all features. And in principle, we could describe this decision function by a Taylor expansion. As a physicist, you do Taylor expansions. But the problem is that you have one root point and then you have lots of higher orders. So it's not practical. So because you would need infinite orders to get your 17th order right? So what we do instead is we do what we call a deep Taylor decomposition. We do a linear approximation around different root points, okay? So which means, and I think I will need some tools to explain this. So I need a manifold, right? Okay, so here's the activity of a neural network, okay? So here's it's some ReLU function or something nonlinear, okay? So every neuron basically is one of these nonlinear functions, embedded in some space. Learning makes them, linear or non-linear, or orients them and puts them somewhere, right? That's all. And so the idea is now, for every neuron, if we take the right root point, not the same root point, but different root points, then we can make a linear approximation and formally prove that this approximates the overall decision function. It's a bit of a longer paper if you like to read it. So that means what I just explained here as a rule, as an intuition, is actually something meaningful from the math point of view. And then you basically do this going backwards, but you have to impose relevance conservation. So you cannot get more or less relevance if you go from one layer to the next. Okay. So then, if you train the neural network, and then the neural network says this is coffee. And it says coffee because there's crema. And this is now a kernel method, and it says it's a cat. Sometimes because of the fluffy part here, sometimes because of the mustache. And, cats come in different forms and flavors. Even Johannes just, 15 minutes ago also had cats. So you always have to have cats and dogs, right? So you can see this is usable, right? So basically, whatever neural network you're using, in the light of this Taylor decomposition theory, you can devise a layer-wise relevance propagation rule that is optimal for this condition. So you need to do different things for transformers, for pooling, for whatever, right? So, and it's important to use the right LRP rule, otherwise you're not in sync with the theory. Now, having said this, there's many explanation algorithms now. I think last week they had the World Congress on Explainable AI. It's now a field which has, many hundred participants participating in the conference. So, and we basically were among the first to start it. I would say this was like one of the first papers. Okay, so there's whatever you use, transformers, unsupervised learning, convnets, LSTMs, there's an LRP rule. Okay, so whatever you do, you can find a way to analyze. Okay, so there's books about it. There's a nice review paper introducing IEEE from 21. So now let me just give you a bit of a perspective. So we have now a method with which we can analyze what models have learned, which is nice. So let me just, and this is a 2018 paper in Nature Communications. Where we ask this question. So usually in our lectures we say machine learning is about taking some data and a machine learning model and try to predict well on unseen data. That's called generalization. So then we report the numbers of the generalization errors, and then we are happy. Hopefully we're generalizing well, right? So is that all, right? And of course, because I'm asking the question in the following way, maybe it's not all, right? Ideally, right, if we could measure the generalization error extremely precisely, then everything would be fine, perhaps. But what I'm trying to show you is that it's not as easy as you may think. So this is a model that was also trained on computer vision. It's a classic data set. It's called Pascal VOC. It has served the computer vision community for a decade, right? So typically in computer vision, you have these tables, right? So where you have your data set and then you have, say, two or more models where one is yours. And if your model is always the best, then you write a paper and it gets accepted in CV per hour or something like that. It's a bit shortened. So now we can see that, both models are pretty good. Sometimes there's a difference, right? And for example, here, for the horse class, it's very good in generalizing, but the numbers are not very far apart. So from all we have learned is this generalizes well. So we are happy with both models. But I will show you why we should be a bit suspicious. And so here is a new picture that is given to the model. Both models say it's a horse, right? But now we analyze what the horses use in terms of solving this problem. So this one is the deep neural network, and clearly the model is focusing on the horse's butt, the rider, the nose of the horse, so the object. So that's good. This model, however, looks a bit to the horse's butt, but also looks at the lower left corner. And I don't see a horse. But there is actually a copyright tag here, which says Lothar Lenz Pferdefotoarchiv.de, which is basically a copyright tag saying that this is from a repository with horse pictures. So this is a data set, which is classic, being used by the computer vision community, as I said, for 10 years. But no one looks at every data point. These are millions, right? So it just happened that a large number of the horse class pictures were having that copyright tag. So this model was actually making use of this copyright tag to solve the problem correctly, and this one wasn't, right? This one understood the task, right, which is recognizing objects. Okay, so you see that the generalization error tells you nothing about what you see here, right? So that brings me to this horse, and the horse's name I may introduce. It's called Hans. Hans was a horse in Berlin, 1904 or something like that. And Hans was very famous. It was world famous. And because Hans could do math, okay? So here on this board, you see math exercises like 3 + 2, okay? So the human would point at one of the squares, and then 3 + 2, Hans would give 5 taps on the wooden board, okay? Hans would always get it right. And journalists, they were so excited. Journalists all over the world said, horses can do math. So it cannot be so hard, people. Horses can do math. And then somebody with more reason than journalists came and said, well, perhaps it's more than, being able to do math. Maybe the horse is actually sensitive to the human. And then they exchanged human by some other random human, but the horse can still do his task. So Hans was reading the human and solved the problem by reading the human, not by doing math, okay? This is why everybody called this horse Clever Hans. So coming back to this. So this is really what we call Clever Hans behavior, solving the problem correctly for the wrong reason. So if we have something more interesting and maybe more critical than recognizing horses from cats, like you would do medical diagnosis in cancer, I think no one would like to have this model. We all would prefer this one. So what I'm trying to say is there's lots of models out there. My estimate is that perhaps 50% of the models out there in academia and industry are of the type Clever Hans. So the algorithm that I showed is a linear scaling algorithm. So there's absolutely no excuse, even if you have billions of data points, to not run this algorithm and to understand the mechanisms and the strategies that the model ultimately uses. It's, however, even worse, and I skipped this from this talk. Nowadays, people have foundation models. In foundation models, we are actually using unsupervised learning, for example, self-supervision, for creating a foundation model. And then we use that the representation of that foundation model to solve downstream tasks. So just this paper is from 2019. From 2 months ago, we had a paper in Nature Machine Intelligence where we showed that also in unsupervised learning, we have clever Hans. So this means that virtually all foundation models are corrupted by that, unless, and then you have to read the paper. Okay, so we're, okay. Yes, very good question. I'm not going to cover this, but you can, for example, in the classification task, you can look at the red pixels, remove them, and see when the classification breaks down. That's called pixel flipping, and it gives you quantitative results, and there are many others, but this was the first one. Okay, so we have now established a technique which allows us to understand what our models do. Now we can shift gears and go to the sciences, because we are equipped to understand what our models do, because in the sciences we don't want to do nonsense. Okay, so here's the Schrödinger equation, and you have seen that before this morning. And the interesting thing about the Schrödinger equation is that it looks very innocent, and it's very hard. It's really a bitch. You cannot compute it analytically unless this is a hydrogen atom. So it's very hard. So what people did was they thought about approximations to the Schrödinger equation, which boil down to things like density functional theory, which got Nobel Prizes and so on and so forth. So these are basically approximations to solving the Schrödinger equation. So in 2011, I had a sabbatical at IPAM, Institute for Pure and Applied Mathematics. If you get invited there, please go. Right? So it's a bit like Oberwolfach. However, you're entitled to stay there for 3 months with about 30 other people that also stayed for 3 months. And in the sabbatical, you usually go somewhere and everybody's busy. But this time, there were 30 people that were entitled to stay there and do interesting math and science. And this gave some interesting collaboration. So I heard people talk about this. This is quantum mechanics. I'm a machine learner, but I was trained in quantum field theory, string theory, and quantum mechanics. So I thought, why not? Instead of solving these equations and then making some gross approximation, why not treat this in the first place as a stochastic problem? So we generate some data about some molecules, say, their quantum properties, and we try to shortcut the Schrödinger equation. That was the idea. And we published a Physrev letter. Well, we submitted a Physrev letter during the program, so within 2.5 months, because it worked. And they even accepted this. So this become, and I will tell you the details. So first thing in machine learning is always that you need a representation. You need to have some features. So this is not a picture of a dog or something. So it's molecules. So you have a bunch of atoms, and so atoms live in 3D space. So you have, say, if you have 10 atoms, then you have 3 times 10 dimensional space, and you have some quantum properties like energies, band gaps, all the typical quantum mechanical properties. So how do we represent this molecule? We represent this molecule by taking the Coulomb force between the ith and the jth atom. That was our first guess, which is not so far away from physics, right? Which means that you get a matrix for every molecule. You do some zero padding, so that you can have comparable matrices. And then you put something on the diagonal that I don't talk about. So now you want to understand what's the difference in this representation between two molecules. Well, you just take the Frobenius norm difference, and that's it, right? That's your distance between them. And then I insisted that we use the most simple machine learning model possible. And that is nonlinear. That's a kernel ridge regression model, because in the end, if you hear me, what you want to do is you take the features inside and you want to predict energies which are continuous quantities. So it's not a classification, but a regression problem. Okay, so then basically we put in the distance, and then we train a kernel ridge regression model, and that is done in fractions of a millisecond, and then we have our model. So we can put in a new molecule, compute the Coulomb matrix, and get a prediction out of sample. Okay. So nicely, the more data you put in, the better it works. So you can be a bit more adventurous, maybe take other things than kernel ridge regression, like neural nets. And then you come to something like, less than 1 kcal per mole, which chemists call chemical accuracy. So if you want to know about that, chemists are genuinely happy if you can go beyond 1 kcal. So they're fine. So our models are good enough. Out of sample, by the way, right? So now we can ask, and this is now a neural network. It's a deep tensor neural network. It's very complicated, very nonlinear, where we try to look at the local chemical environments of an atom, right? So we try to learn that, given the quantum mechanical data. And then we can try to see how can we explain things. And then we can basically, get these gummy bear plots, which are, the corresponding things of the heat maps that you saw before. And basically, the idea is the following. Assume this is benzene. The model gives predictions for benzene, embeds this into chemical space. Now, assume that you're hydrogen, right? Then, you would make a plot of the chemical potential, and I put this in quotes. And basically, this is a question: where would you like to sit if you were hydrogen? Okay. And here, if you were carbon, right? So you show this to the chemist, and chemists are genuinely happy about this, right? And you can do this, of course, for much more complicated molecules. So this means that the model has learned something that is chemically meaningful. And now I come to the question that we could now ask is can we learn something that is not in the data, that is not explicit there, and that is not in the textbook? So there's some debate about aromaticity of molecules. And we can, for example, ask, aromaticity means that there is a benzene ring somewhere, and then there's some structure dangling from it. So which one is the most stable aromatic thing? Which means that we are doing it, even though there's stuff dangling from it. And so the neural network comes up with its own definition of aromaticity, which is a very nice one. So we can test this and of course show this to chemists. So I urge you to read this paper, and then you can also do this for materials. So this kind of was the paper where we got the prize last year. Okay, so what's the idea then? Like the vision. So in quantum mechanics, if we use standard DFT, or let's say why bother at all, right? So if we use standard DFT, every data point costs 5 hours of compute. in CCSDT, which is a higher level of quantum mechanics, it's about 7 days of compute, right? So to get a data set, that's, you know, a lot of compute. It's no wonder that you know, the chemists are using up most of the supercomputing power with the, you know, weather people or climate people. So how about the following idea? Let's think about the space of all possible small molecules. It's a vast space because the combinatorics in chemistry is extremely high. So there are more possibilities for molecules than atoms in this universe. So, you know, trying to get a map of this space, right, of the chemical compound space, like we as humans got maps of, you know, of our Earth and of the planet's system so that we could navigate. So can we get a map here? And the answer is yes, we can, but it's a bit local, because even if our compute is less than point something milliseconds instead of 5 hours or 7 days, we still have a hard time of doing, you know, atoms of this universe times computation. So, but still we can have some local exploration and we can get a feeling for it. Chemistry has been exploring the chemical space very locally only. Okay, so let me switch to another topic. Navigating chemical space means I get some molecule and I provide, the machine learning model provides the quantum chemical properties. So molecular dynamics is a bit different. Oops, sorry, wrong way. So from the machine learning problem, so let me see, what is molecular dynamics? So assume I have a molecule with 5 atoms, okay? It lives in a 15-dimensional space, and every configurations of these 5 atoms give rise to different energy, right? Even a small change may give rise to drastic different energy. So practically, in this space, in this example, I have a 15-dimensional space and I have an energy surface above that. So now what molecular dynamics is basically, the question is, how does this dance, right? This molecule on a quantum mechanically accurate level. Because then we can compute spectra, we can look at binding, we can do all sorts of questions. So basically for this, you would have to take, you know, sample that space to get an energy surface, and you take the derivative to this energy surface, then you get the forces exist, you know, that every atom feels, okay? And that force, you know, you can run molecular dynamics with, okay? So that's the idea, and that's what we do. So just to give you an idea, and maybe I have to look at the time. So I have some time. So basically, for example, for something like aspirin, which is not very large, we need to sample the space of this energy surface with about 50,000 samples. So 50,000 times, you know, DFT, that would be 50,000 times 5, or 50,000 times 7 days would be a bit longer, right? One would be feasible, one not. So now we can think about this. So because ideally we would like to get the most accurate quantum mechanical, you know, level of theory, but we would like to have our regression model with very few data points. So how do we do that? Because then we can also have molecular dynamics on the CCSDT level, okay? And so if we, again, think about a molecule, right? Remember that. this is a 15-dimensional space, then we can think of some configurations, right? That's basically a point in this energy surface, and we can take the gradient, which gives us the forces, right? So we can also compute the energy and the forces, and then do a model that predicts energies and forces. Okay, it's a bit more involved. The interesting thing here is that if we do computer vision, then we're trying to estimate a vector field. But here we are interested in a vector field that is curl-free. So this is a vector field where energy conservation holds, because it's physics, right? So there's a differential equation that we know, okay? And so the Stefan Schmiler, who's a postdoc now, he's been the first author on many of these papers that were done together with Alex Tkachenko's group. Okay, so adding that knowledge. So first of all, we add energy conservation, but also we know other things. We know that molecules are symmetric, right? So they are rigid and non-rigid symmetries. And if we add all of this up, right, then we can actually reduce the number of data points drastically, right? Instead of taking 50,000 data points, just putting in energy conservation, so which means our model is only learning on the manifold of energy conserving models. We only need 1,000 data points, and if we are including symmetries, then we only have to have 100 data points. So 100 times 7 hours, 7 days is feasible, which means that we can bring quantum chemical molecular dynamics to a new level. At DFT level, we're often not getting the ground states correct, or the transitions right, or the reaction coordinates right, and things like that. So if we can do this on the higher level of theory, then all of a sudden, we can predict things from the experiment. And we can do that. And there's a lot of things that we can start predicting, like rotors coupling, steric repulsion, this is for the connoisseurs, electronic transitions, and so on and so forth. All of a sudden, this is available at the accuracy of an experiment. Okay? And there's code. Now, 2020, I had a sabbatical at Google, and everybody had Corona, me too. I was sitting on my sofa, and the question is, what could you do, right? And one thing that is complex, as I said, computationally, is to get force fields for your molecular dynamics, because it takes a lot of compute, and say something of the order 50 to 100 atoms takes about a month of compute, roughly, right? Because you need to sample the points, and then you need to compute the model. Sampling of the points and doing the quantum calculations, that is most relevant in terms of time. Now, because we all suffered from the spike protein, or the SARS-CoV-2, so we thought, how about modeling the receptor binding domain of the COVID-related molecule? So that, of course, has more than 10,000 atoms. And our assumption, our scientific hypothesis was to say, well, why is it that this is so contagious? It means that this virus is binding very tightly, right? Much tighter than other diseases, okay, other viruses. And so then we thought, okay, 10,000 atoms, in some accurate quantum chemical calculations means that we have to take 10 weeks as a basis. There's a factor of 100 between the 100 atom system and the 10,000 atom system. The computation scales as n to the 5 on the right level, which means that's n to the 100 to the 5 times 4 weeks, which is easily age of the universe given some nonlinearities in the process. Then we have one data point. So since Google didn't have that kind of compute, and since I was, thinking that, retirement will be in 10 years or so, right? So I thought we have to do something different. So we thought about the following. How about taking the large protein or the large molecule and dividing it up into smaller sections, right? And then making local models, right? Because that takes much less compute because n is much smaller. And then what? Then we need to, put the local models together. The problem is physics is not only about local stuff, but life wouldn't exist without long-range interactions. So no protein would fold without the van der Waals interaction, which means that it's running too short just to build local models and putting them together. So which means that we have, we took fragments and learned local models, but then we also took larger fragments and tried to make the model learn also long-range interactions. And we put some physics inside and so on. So in the end, we took a novel machine learning architecture that we developed. It's called SpookyNet. It was the first transformer in quantum chemistry. Then we put all our physics knowledge inside, and then we did a bit of compute, right? Don't ask me how much. There were 3 million compounds that we needed to compute, and we gave them back to the world so you can download them, right? So, and that came in this, that's this paper. So in other words, we have some small molecules, so we learn the local models from them, but also we have some larger molecules, molecular fragments in water, because protein chemistry is in water or in solution. And then we have this model that puts this top-down and bottom-up fragments together and learns how to make sense of this. Oliver Unke is the first author on this paper. He's my colleague at Google. So the idea would be that you have this water box around your molecule, then you select a region, you cut a sphere, you saturate the bonds, and then that would be the top-down fragments. And you typically will have 1 or 2 layers of water around the protein fragment. And these are just enumerations of the small graphs. And yeah. So that's a lot of molecules that we computed. And now I can show you a bit of, I hope this works. Ah, okay. So now I wait. Okay, so you say, why did you waste all this supercomputing and develop this model? What is it good for, right? In the end, of course, we want to understand this spike protein, but how can we know that we are right? Okay, and there's the Drosophila of chemistry, which is like alanine 19, which is some molecule which is has 300 atoms or so. So it's possible to compute it still with some time, and then you would take some configurations that alanine, in this case it's 15, has. And then we run the model. We do molecular dynamics. And this is in vacuum. So you can see this folds. Okay? So this is interesting. But you say, well, there's AlphaFold. Why the hell do you do this, right? So it's like you going to the movies. In AlphaFold, you get the first picture of the movie and the last picture, but you don't get the movie, right? So molecular dynamics tells us about the dynamics of that the molecule has, the reactions and everything. So I'm not saying, just to get me right, AlphaFold is fantastic, right? So it solved a very, very important problem. But here we want to see more. We want to go towards protein interactions and things like that. But now we can take some of these configurations, compute the quantum chemical properties, and see whether our model gets it right. And we are at 1 kcal per mole, whereas any classical force field is about at 60 kcal per mole. The other thing that you know, the connoisseurs of you have possibly seen is that this folds into an alpha helix. But if you look very closely, you can actually see that it folds also in a 310 helix. So it's actually oscillating between alpha helix and 310 helix, something that experimentalists have shown, but no classical force field shows that. So since experimentalists have shown this is the truth. So our model is the one that gets this right. And interestingly, a lot of several colleagues have reproduced this result. So it's interesting because we can see how the folding works. Okay, so just to give you an overview, we can now, you know, that's the way we do this, and then we can, you know, look at something like crumbene in water, and then we can see what does the molecular dynamics tell us, and then we can compare this to an NMR spectrum, which is the experimental spectrum. And we can also see whether the classical force field and the new method, whether they differ, and they do. And we can also look at the spectra. And you can, I mean, for those of you who know NMR spectra, this is a bit, you know, for NMR specialists, the blue and the orange curve that are in different frequency ranges, they are remarkably in sync, right? So whereas the green one doesn't show any spectral structure. So the NMR people really like this result. Okay, so we can now, I have 10 more minutes, right? I have 5 more minutes, 10, okay. Okay, so now, basically, my philosophy as a physicist is that I want to contribute to the sciences. I want to contribute to the understanding, which means that I really have to think about problems that matter to the community, the chemistry and physics community. So interestingly, it turns out that most of the machine learning methods available, they are not able to answer some of the problems. So we need to push machine learning further. So we need to push mathematics further. And here's Socrates, which is an equivariant transformer. And then you say, oh, equivariant transformers, equivariant models, I don't have the time, right? Because they're extremely slow. So equivariance means that you have, you know, so throughout the model, you know, no matter how the orientation of the molecule is, you get the same results. But throughout the transformations that the model does, which is very useful in physics. So this was quite surprising because this is the Socrates architecture, which is, you know, not even a year old. So Alex, one of the interesting things is about the scaling. So these are, you know, some transformers, right? And that's an equivariant architecture, which has, and I just show you, L plus 1 to the 6. So L is so to say the dimension of the cubic, what's this? Kugelflächenfunktion. Sorry. The YLMs, right? So Sorry, this is jet lag. Socrates has not to the 6, but to the 2, right? So it's a blazingly fast equivariant model. And, you know, there are some tricks, and I have the time for it. But what I can show you is if I compute in molecular dynamics, I want to compute frames per second. How many molecular dynamics steps can I do? So here's Socrates, 300 frames per second. And this is the error, right? This is low error and fast. And these are other models. So you can have slow and not so good, and you can have very good, but extremely slow, right? So this is like a sweet spot. And this is all that, you know, a lot of people are now using new machine learning architectures for doing molecular dynamics. And they're only looking at the errors. And that's not good, because it's not about the errors. It's about whether the model is actually doing a stable molecular dynamics. It's totally useless to have a small error if the molecular dynamics is not stable. As Jakulov's group has shown, is a lot of these models that are very good at predicting, they're very lousy in you know, having a stable molecular dynamics. So they're useless, right? So it's having the sweet spot where you have stability and speed, right? So there was a workshop organized by Alex Tkachenko's group, and they had a very interesting setup. So there were new, they generated a new data set. They provided this data set to people, and then they gave new structures, and you had to predict. In fact, you had to give your algorithm, and they would use their computer to make all the predictions so that nothing could be, you know, done, right? And so this was the T workshop, and there's two chemical science papers that thoroughly analyze it. And Socrates was among there are two models that ended up pretty good, or in the top. That was Maze, some Maze variant, and Socrates. So one very important step here is really that we make an equivariant model that is fast. Okay, so what can we now do? We can look at, you know, very large structures and look at their spectra, but we can also follow our notion of mapping chemical compound space, but now with molecular dynamics. Okay, so it's not about one molecule, but it's about all molecules in a sense. Okay, so let me just say, take this all molecules with a grain of salt. Okay, I'll show you what we have done. And this is a paper that is currently under review, but it's in a minor revision. And so what we do is we take essentially a lot of big data sets that are out there. Then we train Socrates, and we also pimp up Socrates by having a short range and long range interactions in the error function. And so like, and also dispersions and electrostatics. And then we predict forces. So it's really, the paper, by the way, is on arXiv, so you can see it. So we have used all this data set, right? And then we can apply it out of the box because it's a foundation model. We can just apply it to new structures. For example, water. And let's be fair, we are on DFD plus MBD as a PB0 plus MBD. That's not going to be sufficient for water, right? So we have, our model has clear shortcomings on water, but we're very open about it. New has to be done. But this data is PBE plus MBE. Proteins, that works very well. Glycoproteins, lipid bilayers, carbohydrates, nucleic acids. So basically, that's a lot of chemistry. So we are around 1 kcal, right? Sometimes 2, 3. We can look at the spectra. And the interesting thing is that if we are, so in the paper we write that we have a factor of 50 only to classical force fields like EMBA or CHARM or something like that. But of course, there's a difference in the quality, right? So as I said, EMBA CHARM typically 60 kcal, 50 kcal, but we are at 1, 2 kcal, right? So this means that we can look at quantum mechanical properties of a large part of the chemical space out of the box. The model you can download. You can even play with it in a collab. So you can also download the data. Okay, so there's a number of people that actually are already using it. So talking about data, one of the things that I did during the last sabbatical at Google was also to provide a large homogeneous database across chemical space. So the QCML data set, which was appearing in March 2025, has something like 15 million non-equilibrium structures, a lot of 15 billion, sorry, and 33 million DFT results. So it's available. You need a large hard disk. It's about 800 terabytes, but you can get slices of the data. So XAI is important for understanding. SpookyNet, Socrates, and Solar. Solar was the foundation model. So because it's based on Socrates, we call this Solar because it's a foundation model. So including physics knowledge is important, and there's a lot of things that we can now do because it's about trying to understand chemistry and do chemical applications. So we have in the paper, we have a number of chemical applications already, but this is just the starting point. Thank you.
Merci.
Yes.
Many suggestions have been made to you about you have plans to look at the protein-protein interaction.
Yes.
And how the other protein
yes.
come in and affect this folding.
Very wonderful question. So in the GEMS paper, which was the first to look at large molecules, where we did this patchwork blanket idea, where we stitched local things together and learned the global interaction. We actually put this into the discussion section. So we actually looked at some protein-protein interaction because in the receptor binding domain, we actually looked at the ACE2 receptor and computed these things. We also looked at the different variants of COVID and how strongly they bind. But what we found, and this is no new insight. Martin Karplus always said this, the one who got the Nobel Prize. So he said the molecular dynamics is super wobbly, but what we are seeing is it's even wobblier. So this, I didn't know about this at all, and no one knew about this fluctuation between 310 and alpha helix. So it's exactly the direction.
So in the microRNA binding to protein, there are some well-known examples of bipartite structure.
Yes.
Maybe you can look into that.
And maybe we can just look at it with our foundation model. So I mean, the point is, so Alex's group and my group are collaborating on this together with the Google people. And there's so many applications and so many interesting things to look at. It's a starting point. We are able to analyze for the first time in a very high quality quantum mechanical very large systems. So I think and again I was saying that there's about 15 groups that have contacted Alex and me that do different chemical applications. So we are supporting them and giving them help, because it's not so easy for chemists to use things out of the box, although we have tried our best to be able to do that. Okay.
So another question is that for the first part of the talk,
yes,
about where the informative part on the graph, on the image.
Yes.
So do you find that the informative part is stable if you change the different comparing groups? For example, if you look at ladybug, what if you put a different bark? If you put, say, elephant.
Okay.
Will that
informative
part change?
Yes. So basically, I only showed this to the correct classes, but you can show it to all classes. So you not only can show what speaks for a certain prediction, but also what speaks against another prediction. So that's people are using this, and it's very helpful, because if you think about handwritten character recognition, so if you think about an 8, right? So then the model will say, this speaks for the 8, right? Then the model will put this red for the 9 and this blue, right? And so on. So you can, and then that's of course a trivial case, but there in the sciences often we don't know the mechanism, so we can have us informed by our models. So
thank you.
You're welcome. Yes, please.
Yeah, like as you mentioned, when you are training the model and you ask some physical theory and
yes.
it reduce the data set needed. Yes. I want to ask if it means that like when you are adding more data set without adding the physical theory,
yes,
it still comes to the same conclusion, a similar conclusion.
Okay, so it's a very good question. Yes,
and does it mean that the model somehow learned some physical theory inside? I mean,
it's a very good question. So there's if you go to my Google Scholar profile, and it's one of the last 10 papers or so. First author is Max Eisler. So Max is a computer science student, and he believes in large data, right? And so he said, he basically told me, we don't need all this physics, no differential equation, just a lot of data, right? And I said, no, we need the physics, and we disagreed, right? But I think it's not a question of belief, it's a question of research, right? And so he was doing a lot of very interesting and delicate simulations where he used a lot of data, and then, for example, ask a question, did a model that just has learned like QCML size data, does it have energy conservation? Or is it equivariant in the structure? So you can measure this, right? And so you see, the more data you have, the better it is possible to learn that, right? So there's a very interesting and resolved issue. If you constrain a neural network or any kind of learning method, put physical constraints or differential equations or symmetries, then the optimization is harder, right? It's just an optimization thing. And if you have something unconstrained, then perhaps during the optimization, the model can find some unconventional solution that is actually coinciding with the physics. So this is an empirical and theoretical question. So the empirical question we can read in the preprint of Max, right? In the context of computer vision, and natural language processing, basically people come to the conclusion that just more data helps and you don't need to constrain a lot, right? In the case of physics, this is not yet resolved. This is an ongoing debate. The question, for example, if you don't put the physical constraints, then the models are very likely to be not stable in molecular dynamics, which basically is the whole point of the exercise, to be stable in molecular dynamics. So you can get very good predictions, but are not stable. Does it answer your question?
Yeah, and another thing is that if I put enough knowledge and I mean data set inside, and will I be able to kind of extract? So
yes, absolutely. Yes, that's what I with this a bit of clumsy example with the aromaticity. That's one thing where you can get the neural networks theory of aromaticity, which is not worse than the human theory of aromaticity. There's many possible ways to describe this. So it's actually interesting. So we are at a phase where we have data and where we can extract knowledge. We have learned that explainable AI does the job for you. Okay?
Thanks.
A very short question, but hopefully short. In the case of protein dynamics that you showed, do you see a way forward of molecular dynamics reaching the microsecond or millisecond, or is this coarse-grained terrain?
You know, in Berlin, we have Cecilia Clementi and Frank Noé, who are very good friends. And Cecilia is, you know, the coarse grain, you know, super expert. And also Frank is thinking about this long time scale things. I think at the moment, you know, what you've seen in Socrates, that's, you know, 200 nanoseconds or something like that, right? So it takes 3-4 days, right? It's not bad, right? But with a lot of, you know, energy, I mean, compute energy, you can actually also, you know, go a bit further, right? But I think that if you want to go to microseconds or milliseconds, it will still require, you know, some you know, advanced tricks. Coarse grading is one, but you could also do some advanced sampling. You could push the systems, you know, across boundary in a nice way, and things like that. This is ongoing research, and nobody knows how to do it. I also don't know it, but it's totally exciting, and we can already now ask some questions like protein-protein interactions. I mean, that's the question, or just general properties of carbohydrates or something like that, which we couldn't ask before. Okay?
Thanks.